Hello everyone. Welcome to the next section of the course, Representing Data and Engineering Features. In this section, we will go over some common feature engineering tasks and common pre-processing techniques. Then we will learn to represent categorical variables and text using categorical features and text features. Lastly, we will discover the best way to encode images using SIFT and SURF. Now we move on to the first video of this section, that is, Understanding Feature Engineering and Pre-Processing Data. In this video, we will understand the basic concept of feature engineering. Then we will look at some of the most common data pre-processing techniques. Although every learning algorithm has its own strengths and weaknesses, differences in performance often come down to the way the data is prepared or represented. Feature engineering can thus be understood as a tool for data representation. Let's see how it fits in the pipeline. Pre-processing data. The more disciplined we are in handling our data, the better results we are likely to achieve in the end. The first step in this procedure is known as data pre-processing, and it comes in at least 3 different flavors. The first flavor is data formatting. The data may not be in a format that is suitable for us to work with. For example, the data might be provided in a proprietary file format, which our favorite machine learning algorithm does not understand. Data cleaning is best explained as the data may contain invalid or missing entries, which need to be cleaned or removed. Next flavor is data sampling. The data may be far too large for our specific purpose, forcing us to sample the data in a smart way. Once the data has been pre-processed, we are ready for the actual feature engineering, to transform the pre-processed data to fit our specific machine learning algorithm. This step usually involves one or more of 3 possible procedures. Here, the first procedure is scaling. This process brings all features into a common range of values. Decomposition is the next procedure. Feature decomposition is the process of compressing data into a smaller number of highly informative data components. Last is aggregation. Sometimes it is possible to group multiple features into a single, more meaningful one. Depending on the task, this data might be better represented by simply counting the number of logins per user. Let's begin with standardizing features. Standardization refers to the process of scaling the data to have zero mean and unit variance. This is a common requirement for a wide range of machine learning algorithms, which might behave badly if individual features do not fulfill this requirement. Here, scikit-learn offers a straightforward implementation of this process in its preprocessing module. So, we will first import preprocessing module from sklearn. Along with it, we will also import numpy module as np. Now let's consider this 3x3 data matrix X, standing for 3 data points, or rows, with 3 arbitrarily chosen feature values each, or columns. Then, standardizing the data matrix X that can be achieved with the function scale. After that, we can verify that the scaled data matrix, xScaled, is indeed standardized by double-checking the mean and variance. Let's implement it with this line of code. A standardized feature matrix should have a mean value of close to 0 in every row, as you can see in the output. In addition, every row of the standardized feature matrix should have variance of 1, which is the same as checking for a standard deviation of 1 using std function. So here we achieve it by executing this line of code. You can see that we have achieved the desired output with variance of 1. Further, we will look at normalizing features. Similar to standardization, normalization is the process of scaling individual samples to have unit norm. Executing this line of code, our data matrix X will be normalized using the normalize function, and the L1 norm is specified by the norm keyword. As you can see in the output, the X matrix is normalized. Similarly, we will compute L2 norm by specifying norm equals L2. An alternative to scaling features to 0 mean and unit variance is to get features to lie between a given minimum and maximum value. Often these values are 0 and 1, so that the maximum absolute value of each feature is scaled to unit size. We will achieve this using min-max scalar function. On executing the code, we will see that by default the data will be scaled to fall within 0 and 1. Add and execute this block of code to specify different ranges by passing a keyword argument featureRange to the min-max scalar constructor. This is the output that displays the desired values in the array. Finally, we might find ourselves not caring too much about the exact feature values of the data. Instead, we might just want to know if a feature is present or absent. Binarizing the data can be achieved by thresholding the feature values. Let's quickly remind ourselves of our feature matrix X. Let's assume that these numbers represent the thousands of dollars in our bank accounts. If there are more than $0.5 thousand in the account, we consider the person rich, which we represent with a 1. Else we put a 0. This is akin to thresholding the data with threshold value as 0.5. The result is a matrix made entirely of 1s and 0s. Proceeding with handling the missing data. Another common need in feature engineering is the handling of missing data. For example, we might have a dataset that looks like this. There are 3 different strategies to impute missing values which are offered by scikit-learn. First is mean. This will replace all the nan values with mean value along a specified axis of the matrix. Another strategy is median. This replaces all the nan values with median value along a specified axis of the matrix. Most frequent is the third strategy, which replaces all the nan values with the most frequent value along a specified axis of the matrix. Let's take an example of the mean imputer, and we will execute it with these lines of code. This replaced the 2 nan values with fill values equivalent to the mean value calculated along the corresponding columns. As you can see, we have replaced all the nan values with some appropriate fill values. This is known as imputation of missing values. Next, by running this line of code, we will double-check the math by calculating the mean across the first column without counting the first element x as 0 and comparing this number to the first element in the matrix, x2. You can see that the mean across the first column is 3.75. Similarly, the median strategy relies on the same code. So let's execute this code snippet and observe the desired output. Let's double-check the math one more time. This time we won't calculate the mean of the first column, but the median without including x0, 0, and compare the result to x3 as 0, 0. This is the output where we find that the 2 values are the same, convincing us that imputer works as expected. Great! In this video, we overviewed the concept of feature engineering. Then we looked at some common data preprocessing techniques,